Okay, Rasab, welcome back to the second problem. I think Ashmit, you also requested this problem. Ashmit, bro, I sent you so much fucking homework. Like, I get nothing in return. Like, every single piece of my physics CS homework like goes to you. Like, today I'm taking like the most important goddamn test of my life, and I got a text from you, oh, the code is not working. Bro, just Google it. Damn. Um, anyways. So let's take a look at this problem. This is a very important problem in rolling dynamics, rotational dynamics. So let us first just imagine our situation. We have a ramp at an angle theta. Theta is kind of like such a beta angle, Greek letter. What about alpha? No, yeah, I'm positive alpha. God damn it, alpha. Okay. And then we have a cylindrical object to show. Okay, this is the center of mass about which it rotates. Now, just as we did in the last video, when we have something that is rolling, we need to consider one very important point, and that is the point of okay, let me just. God damn it. We consider one very important point, and that is the point of contact with the ground. So we know that this guy is rotating about its axis with some angular velocity, and we also know that it has some velocity this way because it is something rolling down an incline. And since it is rolling without slipping, as we know from the last video, this point right here, there is velocity due to the rotation, which is just going to be omega r, and then there's also velocity due to the center of mass. And since the problem tells us that this cylinder is rolling without slipping the entire time, we know that at every instance in time at which this cylinder rolls down this incline, omega r is always going to be equal to the velocity of the center of mass at every instant. So what that tells you is that there is no friction due to relative motion between this rotation and the ground. This, like this cylinder is not it's not really hitting the ground if it's rolling without slipping. These two are equal, so there's no relative velocity between this point and the ground. Now, you might be wondering, okay, if there's no friction due to that rotation, as there was in the last problem, why is it that when I roll a ball down a hill, it starts rotating, right? Because if we say that there's no friction at all here, there would be nothing to rotate this ball as it goes down the hill. And this is where we get into the concept of rolling friction. So we know that there is a normal force and there's gravity this way, and those two cancel out. Okay, those don't exert a torque or a net force. So that leaves you with this horizontal component of gravity, which we know is mg sine, I wrote theta. I hate theta. Sine alpha. And as a result of this force on the center of mass, there will also be a frictional force. And we call that friction from rolling. Now, conceptually, so if you have a cylinder that's rolling without slipping the entire time, we know that there's this component from the rotational that is contributing to the velocity, and then we know that there's this component from the center of mass. Because of this acceleration on the center of mass, the velocity of the center of mass is increasing. So if you want this thing to be rolling without slipping at every instance in time, this component of the velocity right here also has to increase. Because if this component is increasing due to this acceleration, this needs to increase to make sure that the relative velocity of this point stays at zero. Otherwise, you are not rolling without slipping anymore. And that is the function of this rolling friction. as this velocity of the center of mass increases, this frictional force also exerts a torque, which increases the component of this velocity, right? Because it's increasing this angular velocity, which results in a larger tangential velocity as a result of the rotation. So with that in mind, it's also important to note that, so I mean, this is really a physically non-intuitive thing. Like I view this mostly as a mathematical abstraction, and when I'm tackling these problems, I do so, mostly mathematically. Like, I guess the explanation of, you need something to keep the rotation fast enough such that these two cancel, that is a physical explanation, but it's important to keep in mind that this rotating friction. So rotating friction is the frictional force when you are rolling without friction, without slipping, but there's still an acceleration on the center of mass. That is when you have rolling friction. This is a special case of friction, when there is no relative velocity between this point of contact, but the center of mass is still accelerating, which is what you have in this case. And that is when rotational friction arises. And it's important to note that rotational friction is not mathematically equal to static friction, is not equal to kinetic friction, and is therefore not equal to mu times the normal force. So with that in mind, let's just jump into the calculations. So I'll just start by considering the center of mass to be, but the net force is on the center of mass, so we have mg sine alpha minus this frictional rotation, rolling friction. And keep in mind that we don't know what this rolling friction is. It's not mu times the normal force mathematically. So how do we find this? What we're trying to solve for is this, but we don't know what this is. So how to find this is we consider the torques acting on the system. So if we take the torque about this rotational axis through the center of mass, we can say that I alpha is equal to, and since this rolling friction is going to rotate in the clockwise direction, we're going to say that it's negative. And then it is applied at a moment arm of r. And we know that the moment of inertia of this cylinder is 1/2 mr squared. Now, for instructive purposes, I'm just going to say that c is equal to 1/2. Therefore, the moment of inertia is equal to c mr squared, and you'll see why towards the end of the video. So that being said, we can say that c mr squared alpha is equal to negative FR. Now, since this is rolling without friction, we know that the velocity of the center of mass is equal in magnitude to omega r at all points, right? So to get rid of this alpha, what I'm going to do is take the time derivative of this expression, and that tells me that the acceleration of the center of mass is equal to the angular acceleration times r. A is the derivative of v, alpha is the derivative of the time derivative of omega. So plugging that in, I get that so alpha is equal to ACM over R. Now be careful here, this is the magnitude of alpha. And we said that the frictional force acting clockwise is going to be, the frictional torque acting clockwise is going to be negative, therefore alpha will also be negative. So we can say that CMR squared times negative ACM over R, which is going to be alpha, is equal to negative rotational friction times R. And then simplifying this expression, these R's all cancel out, and we get that negatives cancel out, and we get that the rotational friction is equal to Cm times the acceleration of the center of mass. Okay? Just move this. So, going back to the net force on the center of mass, we can say that MACM is equal to mg sine alpha minus the rolling friction, which is just going to be C times the mass times the acceleration of the center of mass. Simplifying, we get that the acceleration of the center of mass is equal to g sine alpha. God damn. Sine alpha all over 1 plus c. Now, this is a very, god damn, I can't get right straight. One plus c. Okay, calm. One sec, just give me a moment. Acceleration of the center of mass is equal to g sine alpha all over 1 plus c. Now, this is a very, very important equation because this tells you that the acceleration of the center of mass of a rotating object going down an incline is directly proportional to g, a constant, alpha, which is the angle of incline, and 1 plus c, which is not the rotational inertia, but is the constant that comes before the rotational inertia. Right here, 1/2. We said that c is equal to 1/2. So if you have any object that's rolling down an incline that is defined by, that has its rotational inertia some constant times mr squared, it only works when it's mr squared. If this is mr cubed, if I is equal to some constant times mr cubed, this equation no longer works. But if you have any object, and most of the objects, in the class in mechanics that you deal with have a rotational inertia proportional to r squared, mr squared, then this equation works. And it's interesting because it shows you that the acceleration of the center of mass down an incline of a rolling object does not depend on the radius and does not depend on the mass. So if you have a humongous cylinder, like 1,000 meters in diameter, rolling down an incline, and you have a super small cylinder rolling down an incline, they will reach the bottom of the incline at the same time, which neglecting air resistance, because the bigger one will also have more surface area and then there's more air resistance. But if you don't consider air resistance, they will reach the bottom at the same time, which I think is a pretty non-trivial, counterintuitive, and interesting result. So applying it to this problem, we're trying to find the acceleration center mass of a cylinder where the constant is 1/2. So you just get that the acceleration of the center of mass is equal to g sine theta, 1 to g sine theta over 3. And then when you plug that in, I'm not sure what number you get, but you just plug it into this and you'll get the right answer. So yeah.